But now we're going to talk to, well, I'm not going to be, you're going to hear Danilo talk about observability, which I found, I don't know what you're going to talk about. It's very interesting. So please welcome Danilo.
Thank you. Good afternoon. Thank you for being here. So my name is Danilo. I'm part of the evangelist team in Amazon Web Services. And since AWS Lambda was launched a few years ago, I'm really passionate about serverless because I think serverless is showing us the direction where software development is going in the future. Something easier to build, focus on the business logic that you want to build. And talking with customers that build amazing stuff on top of serverless technologies like Comic Relief in the UK or Capital One in the US, I noticed that the feedback that they give to me is that, okay, I have this big application with lots of functions, lots of services interacting with each other. But for me now, it's harder to understand what is happening, if my application is working or not, because there's lots of moving parts. And that's the idea that brought me to create this presentation. So observability for serverless apps and understanding what we should look to understand if our application is working correctly. And the reason is not just for this is a problem not just for serverless applications. Lots of customers are moving towards a microservice architecture. This is something that we did in Amazon around 2001, 2002. We started to decompose our monolith into smaller components. And we see lots of customers going in this direction. And the reason why microservices are so useful is not that we are bad programmers. It's really that this is how the law of nature works. In fact, there's a science, a new kind of science that has been created in the last 20 years. That's the science of complexity. And they are studying complexity and the emergence of complex systems from simple components across lots of different fields: mathematics, physics, biology, social science. And the common trait that they found everywhere is that when there are lots of dependencies among simple components, then there are side effects that adds up and create complex behavior that you wouldn't expect. This is the same thing that happens when there is a traffic queue and you don't understand why there's so much traffic in that specific point in time in your own town. So if this is not something that we can fight, it's really a law of nature, it's really important to decompose with clear interfaces our software so that when we touch something, we solve a bug, we add a new feature, we are limiting the impact of this change in our code base to something that is far away. If I have a monolithic application, it's very easy unless you are a very good programmer to create side effects. With microservices, it's much easier for everybody to isolate the effect or the changes that we make. And this is why we use also microservices inside Amazon and inside AWS. So who here knows Amazon SQS is a message queue service? It's a very simple service where you can put message in a queue and then you can retrieve these messages and process these messages asynchronously. It's very popular with our customers, but also Amazon Retail is using this service a lot. Every time there's a purchase on any Amazon e-commerce shop in the world, a few SQS messages are exchanged to process that purchase. And this is the internal architecture that is based on microservices. So as you would expect, there is a front end where you put the message and get the message. There is a backend that is actually a two-layer of microservices because it's actually composed by lots and lots of clusters where we persist the messages. And a queue can use one or more clusters depending on how much throughput, how much traffic there is in the queue. And the metadata service is mapping a queue towards the one or more clusters that persist the message in the queue. And then this information is stored in a database that now is DynamoDB, our NoSQL database. In the past, that was Oracle, but we replaced it since everything was encapsulated very well. It was not so complex. And then there is a load manager that is monitoring the use of the storage nodes of the clusters by the queues and then deciding if you need to add a new queue or move a queue from one cluster to another. And this is overall the same architecture for the last 12, 13 years, but probably there is not one single line of code that has stayed the same. We completely rewrote everything multiple times, probably. And the reason we were able to do so is because the interfaces between these modules are standard, well-defined, and we can isolate any change. For example, a couple of years ago, the engineering team of SQS had an idea of changing the way we were storing the messages we're talking about, on average, we have a few millions of messages any second or every day going through this architecture. And then they had an idea of changing the way we were persisting these messages in the cluster. And this idea was very, very efficient, but changing a storage layer in production with millions of messages flying is not easy. But we could do that easily because this was running on a well-isolated interface. So we could just create the new cluster node with the same interface as the old one, just more efficient. On SQS, messages can be persisted for a maximum of 14 days, because this is a queue, it's not a database. So we, at some point in time, the load manager was adding a new cluster with the new architecture aside of the others. They were speaking the same language, the same interface. And after 14 days, all messages were running on the new clusters because the old messages were deleted, and we could shut down the old clusters and we replaced it completely, the architecture running in production. So this is an example of why microservices is useful in production and can help you evolve your architecture in an efficient way. And when you build with microservices, probably the most complex part is starting, because when you start, you don't have clear what are the boundaries of the microservices. So my suggestion is maybe it's even better to start with something a little bit more monolithical at the beginning and then you decompose, than to try to overcomplicate your architecture at the beginning, designing something super clean when you will discover that it is not. And the reason is this very practical law. This is Systemantics. It's probably the seminal book for system theory from the 70s by John Gall. And one of the sentences of this book is now called Gall's law, because it's very popular. It says that a complex system works only if it starts from a simple system. And you can't create something complex from scratch. You need to create something simple, and then you must evolve. And this is something that I think relates very well with serverless, because with serverless you can easily create a prototype with like a minimum viable product, and then you can add multiple features on top of that. And that's also the approach that we use in AWS in other fields. So for example, S3, a service that has been talked about today multiple times, it's an object storage. And when we started in 2006, we explicitly wrote in the press release that S3 was built with a minimal feature set. We wrote it and we created with the minimum amount of features that would make it usable, but then we added complexity afterwards. And in fact, S3 started with an architecture that was relatively easy with 8 microservices, and now it's more than 200 microservices that monitor things like lifecycle management, encryption, and so on. So we see these architectures that in the past were a single monolith, probably Java or .NET most of the times. They are evolving into lots and lots of small and granular services that are built using a polyglot architecture with different languages, and they run in different technologies. Something runs in functions, something runs in containers, something runs in VMs. In fact, my experience is that most of the successful architecture are not purely serverless or purely containers. Often they start to mix and match different features together depending on what they need. And the problem with this architecture is that it's very easy to build a network of connected black boxes where every object is doing their own job, but you don't know what you're doing. So my first suggestion today is really think that observability is a responsibility of who is building the software. It's not something that you instrument at the end, like monitoring in the past. It's something that you have to think when you build the application. But what is observability? So observability actually comes from control theory. That is quite an old branch of mathematics. 50 years ago, Kalman, when he was describing a dynamical system, he started to say, we need to introduce this concept of observability. And the reason is that when we use control theory, we need to measure something. Let's make a very simple example. So with control theory, normally we have a desired value, and then we have a process variable. So the most classical example is the thermostat that we have at home to set the temperature of our house, or if you prefer, the thermostat of your oven, where you set the temperature of the oven. You set a set point. I want 20 degrees Celsius, 70 degrees Fahrenheit for my house. And then we have some measurement that check the temperature in one or more places inside your house. And then you need to measure the distance, the error between what you measure and your set point. And then you have to take actions to correct this and reach the the correct values without going too high or too low with the temperature. Even the most basic example, the thermostat is not so easy, and probably lots of you fought in your houses with the thermostat because it was too hot or too cold. And this is something that happens everywhere in a cloud architecture, because as a provider, when we create a service like S3 or DynamoDB, normally we have two main components. We have a data plane and a control plane. The data plane is where you use the service. So you write on S3, you read from a DynamoDB table, you use an EC2 instance. And then there is the control plane. The control plane is what you use when you configure the service. So for example, you create an S3 bucket, you change the encryption of configuration of an S3 bucket, you change the throughput of a DynamoDB table or move it to on-demand. All these changes change the reference set point, and then the cloud provider needs to adjust and find the best way to reach the configuration that you did. So for any application is critical, and this comes, as I said, from control theory, to have the possibility of measuring and understanding what is happening. And the best definition of observability in this scope, I found it on Wikipedia. That's relatively strange because normally I prefer to go back to the sources, but this is probably a translation of, in English, of the mathematical formulation in the previous paper. And this says that observability is a way to measure, is how easy it is to measure the internal state of a system, how much you can get insight on the internal state of a system from its external output. So when you build an application, how easy is to understand if your application is working? It's too easy to understand how many transactions, business transaction is doing, how many data is processing, and so on. And that's the reason why observability is something that the developer should take care and not someone that at the end takes the application and needs to instrument before going in production. And normally when we talk of observability, there are multiple layers. In the IT, normally there are three main layers: the network, the machine, and the application that we want to observe. From a cloud perspective, the machine is really split in two because the hardware is normally fully managed by the provider. The operating system, it depends on the service you're using. For Lambda, we manage, for example, everything. If you use EC2, the operating system is something that you have to manage and update yourself. So it's not really a single layer here, but almost. And on these different layers, we can plug the three pillars. So here I'm using taking some ideas from this book. This is a free book from Cindy Sridharan that I suggest you to have a look at, that talks about what are the challenges of observability with distributed systems. And the idea is that we want to have these three pillars. So we want to be able to get event logs from the application. We want to have measurement metrics that tell us how the application and the network and the machine are doing. And then finally, there is tracing that can help you connect the dots together for a distributed application. So with tracing, you can really understand how a single interaction is going through different components and put that together. Normally, when you start to connect and collect information for these three pillars, you can start also just with logs, because normally with logs, you can create a filter that can extract metrics from the logs. So if you're logging some information that is in some form numeric, you can filter this information and transform that into a metric. And if your log implement one that is probably the top best practice for a distributed system, to have a correlation ID that correlates logs of different microservices of different components of your application that are working for the same business transaction, then you can use the logs even for building a basic tracing of your architecture. And on top of this, you can start to get the benefit. So with log, you can aggregate and run analytics on the log files. So aggregation gives you the idea of what is happening, and full text search is normally very important to find the error and what was happening before and after a specific error. Alerting is built on top of metrics. You can create alarm that tells you if something that you're not expecting is actually happening. And from tracing, probably the best use is to go with visualization. So to visualize the overall architecture and the flow of the data across your application, because as humans, visualizing things is the best way that we have to understand what is really happening. And on AWS, we work to implement lots of features so that you are able to do so. So, for example, with serverless and logs, one thing that a tip that I often give to my customers is use filters to extract metrics from logs, because it's the best way. Don't post direct metrics on CloudWatch. It can be more complex. More recently, we also updated CloudWatch Insights. Now you can analyze and create complex queries on top of multiple log groups. So it starts to be really useful for complex analytics. And one thing that is really important here is dashboards, because having a service dashboard that tells you what is happening for your application is super important. In fact, one of the problems of observability with distributed and large-scale application is the volume of data, the volume of information that you get. That's why we are exploring this idea of using machine learning to improve the way you can observe your application. And we have currently in open preview a feature that is using anomaly detection to help you understand if there's an anomaly in the data that you're collecting. So you can use anomaly detection for metrics. So when you have a metric, it can be, for example, the number of invocation that your function is normally having during the day. We can help you create a range that, based on the last 15 days of data, tells you what is the expected range of this metric. And in this way, you can immediately understand if your metric is going as expected or not. And then you can also set an alarm based on anomaly detection. So normally, an alarm is based on the metric. So you can say if I get too much latency from my API, then this is an error. And you have to set an explicit threshold. Here you can just set an anomaly detection error and say if the behavior goes a certain number of standard deviation far away from the expected behavior, so 2 standard deviation, 3 standard deviations, normally 3 is quite a lot to be far away. And then you can trigger an alarm if you're outside of this band, or if you are just above or below the band. And in this way, you can process more information using machine learning to find anomalies in the data that you collect. And as I said, this is an open preview. So normally, this is the phase when we get feedback from possible customers. So if you're interested, we really look forward to get what you think about this approach of using machine learning in an easy way. And as I said before, tracing is probably the most important power that you have to implement for a distributed architecture. So the possibility to drill down across the different nodes, different services and interactions of your architecture, and being able to understand for each of these interactions what is the distribution of the latency and eventually of errors that you can get when you interact with these other services. And when you start to enter into this level of detail, you get lots of information. So I think it's very important to understand what do we mean by systems performance, because sometimes when I talk with people, it's not clear if something is fast or slow because there's no way to compare what we're building today with what we were building 5 years ago. So systems performance, this book by Brendan Gregg, I think is very good in giving you the understanding of how performance works and what you should expect. And there is this table that I love because it really gives you an idea of what is the latency that you should expect depending on the part of the infrastructure you're interacting with. So if you're inside the CPU, we are in the range of the nanoseconds. If you're in the network, we are in the range of the milliseconds. If you are outside of and doing, for example, a reboot of a machine, you're in the seconds or in the minutes. And it's very interesting if you compare this changing the scale. So for example, if you say, let's imagine that one CPU cycle is 1 second, we get that getting outside of a CPU to access the main memory, something that normally we perceive as very fast, now the RAM of a computer, is actually 6 minutes. And if we go on the network from a CPU perspective, is years that are happening while the CPU is waiting for data to come from the network. And a reboot, of course, is millennia, so it's really outside of the scale. So this is, I think, gives really a good idea of what we should expect. But even more important is that when we start to look at latencies and time inside our architecture, we shouldn't expect single values. It's really impossible to talk about the interaction between 2 services with a single value. So you can't, inside Amazon, for example, say, hey, my maximum acceptable latency for this API is 15 seconds or 3 seconds. What we use is p numbers, so percentiles. And the idea is to look into the percentiles that compose, can be extracted from multiple observations. So, for example, the P50 means that is the value where 50% of the observations are below that value. And it's normally the median. P90 gives me the value of latency, in this case, where 90% of the observations are below this value. P99 again, and P100 is, of course, the maximum, so the maximum observation that I get. And then you can get a pattern like this, where the median, the P50 is probably half a second. P90, so 90% of the observation is around 1-2 seconds. And then we get P100 that is 24 seconds. So really, these P numbers tells you much more about what is happening with the service and what it can be acceptable or not for your application. Actually, this graph is taken from an internal microservice in AWS. Can anybody guess which service is this? This is one microservice of the EC2 autoscaling. And the reason why it's in the control plane, so when you configure autoscaling. And the reason is because most autoscaling groups are in the range of the 1-2 digits of instances, but we have a few customers that have thousands of instances of virtual machine in the same autoscaling group, and very, very few that have hundreds of thousands of virtual machine in a single autoscaling group. So updating takes much, much more time. And if we were to say our maximum limit is 3 seconds or 5 seconds, it would make no sense for this use case. We really need to think about P numbers. So if we use all this information together with the help maybe of machine learning, then the overall idea of observability is to catch something happening before it's too late, so that you can get something in the degraded state, that is the first anomaly that you can check, before you reach the outage when your overall architecture is impacted by this problem. And to do that, I think we should also look at not just at the technical metrics that we usually look at, like CPU, memory, network, but we should really look at the application. This is Nora Jones. She used to work for Netflix at the time. Now I think she works for Slack, but she's a great expert of chaos engineering. And when she was presenting here, she was at reInvent, our conference in Vegas a few years ago. She was telling us about how they deploy in Netflix. And in Netflix, they look at the number of play per second. So how many times a people is clicking play in front of Netflix at each moment of the day. If during a deployment, this number of play per second is affected without any explanation by the deployment, they understand that something unexpected happened, they roll back, and then they investigate what was caused. So if you have a business, look for 1, 2, maximum 3 business metrics that tells you if your application is working, maybe the number of sales per minute, the number of search in a product catalog, and so on. And put that into your dashboard together with your technical metrics. And if those are affected by a deployment or from anything that is happening, that's the best signal to understand that something wrong is happening in your application. And how this is related to serverless? Serverless is probably an extreme case of a distributed architecture where we can really distribute the business logic across lots of different functions and integrate with lots of different services together. Serverless, I would like to add my own definition to the field. In my perspective, is really the capacity of building application without having to think about the infrastructure. That's, I think, is my best summary when I have to give it. And what I like to look at how serverless works. Because when we talk about a serverless application, on one side we have fully managed services like storage, database, and these services like S3 or DynamoDB have been there for years before we were using the term serverless. No, S3 has now 13 years. What changed is when we start to have functions like AWS Lambda, because with functions we can put our own unique business logic on top of these fully managed services, and this creates serverless applications. But how do these fully managed services and the functions talk together? They talk together via events. So I think events are an underrated component of serverless architecture that we should talk about more. And events is really what is linking all these components together. Because, for example, I upload a file on a storage system. This file is a function that is analyzing this file. Maybe it's an image. I get some metadata. Then I store the metadata in the database. And when I store on the database, this file is another event, and maybe another function can group together multiple information from that database and prepare some static content to optimize the performance of my application. So this beautiful chain of events is really where you can create interesting serverless architecture. And events are super important. But what are events? So if we look into the dictionary, an event is something that happens. Pretty generic. But actually, in an IT architecture, is something very precious, because events tell us a fact. If a user created a new file, this is an immutable fact that cannot change in any way. In a distributed architecture, anything that is immutable is super easy to use. Anything that is mutable, information that can be updated, is super complex to use, because when you get this information, maybe someone else in another part of your architecture changed that value, and it takes some time to propagate. So events are really useful to share, because are immutable facts about what is happening in our architecture. And they also form a nice time series. So you can easily order them. And this tells you, OK, at this point in time, a customer has been created. Then he created an order. He paid successfully. And then the customer updated the address because he discovered that it was wrong. So this is a way to look at our architecture from a completely different perspective than traditional monitoring. And modeling events also brings you to think more about time. And in distributed architectures, time is really important, because normally we were used to develop everything locally, like on our laptop, and everything seemed to happen synchronously. Everything is super fast. But when you deploy in production, and especially if your architecture is distributed, time becomes important, and latency becomes part of the way you have to think how to send and share information with other components of your architecture. So events help you think in this perspective that is slightly different. So how can we help event management for a serverless application? This is something that we were thinking about for some time in AWS. So one first thing that we did was based on the concept of nested applications. So let me just explain what I mean by serverless, by nested application. When we talk with our customer, we realize that there's lots of common problems that they're trying to solve. But these common problems, they require some customization. For example, one thing that mostly every customer wants to do is to monitor social media, monitor Twitter, and if their brand is mentioned, they want to act on this tweet. Some customers want to store the tweets and do some analytics. Other customers want to check the sentiment of the tweet, and if it's negative, they send it to the customer support for an immediate reaction. So it really depends on the customer. So building something similar serverless is super easy. It's really almost serverless 101. You have some way of scheduling your Lambda function, for example, every 5 minutes. You can use CloudWatch events. And then you use the Twitter search API to search if your brand is being mentioned. Then you need some place to store the last checkpoint of your search so that the next search starts after that checkpoint to see if there are new tweets. And then if you find tweets about your product, you want to pass those to a Twitter processor that does something that it's unique to the customer. So this part here is a completely standard component. But probably most customers can just use this as it is. And the Twitter processor that is reacting to the tweets is something custom that every customer wants to do that differently. So the idea is that we create, when we introduce the concept of nested application, is if we can create this standard component, then you can, this is an example of infrastructure as code. This is a SAM template. You can say inside this my application, I want to nest another application that is the Twitter event search source app. And then this application that I embed as a black box will search for some text and then will pass the tweets to my function that I customize and create from scratch for my own purposes. So this is an approach that we launched now some time ago, and it's starting to pick up with some interesting use cases. And one of these is exactly related to events. So we created this project that is completely open source. It's called the Event Fork Pipelines. And the idea is that when you have an event-driven architecture, you probably have something like a pub sub topic. On AWS, you may use SNS to do that. And then you process the event from this topic. So for example, maybe your customer orders, they are posted here, and then you get the order and you process the order to start the delivery of the order. So again, here we have how you process the event. You use your own custom business logic. We can't do anything here. But since this is a flow of events, we created standard components that you can nest inside your application to store and backup the event, to analyze them, and eventually also to replay the events. For example, in case of a failure, you can replay them to see in another environment, like a test environment, or to fix the error in production. And those are all built using standard components. So for example, to store and backup, and this is probably the most interesting one from an observability perspective, you pass the event to a Lambda function, and then it's using, in this case, Kinesis to store everything on S3. You can eventually optimize the format to be, for example, Apache Parquet, and then you can use Athena, as we saw in a previous presentation today, to run SQL queries and analyze your events and see what was happening if there's any pattern there. The search and analytics pipeline is similar, but in this case, instead of S3, we're using Elasticsearch so that you can use Kibana or your favorite tool to search and analyze the events, a little bit more costly probably. And then an SQS queue is used just to replay the events in case you want to replay the events in another environment or in the same environment. This whole solution is available, as I said, on GitHub, and it's also available through the serverless application repository, so you can install it and check it, each component or all together to see a sample application. Can we help more? So we really think that events should be a first citizen in a serverless architecture. So in July this year, we launched this new service that is called Event Bridge, that is built on top of CloudWatch events. And the idea of this service is to integrate also with external application from software as a service providers, like a trouble ticketing application. And this event, when they are shared, they have a standard format, like a detail and a source, and then can contain a detail type and a source, and then they contain some specific information. And you can create your own rules to route these messages to a Lambda function or to a Kinesis stream to store them. So for example, this is a rule that says everything that comes from this partner, then maybe it's my trouble ticketing partner, must be processed in this way. Everything that is for the billing or fulfillment department must go to this other route. Anything that is a resolved ticket must go into this Lambda function or so on. And we work with lots of partners that are already integrated with this platform, and we also open for onboarding. So if anybody here is a software as a service company or represents a software as a service company, we have an open onboarding for being integrated with this platform. And you can use this to react. So for example, a trouble ticket has been created. I want to react with my own business logic. You can apply intelligence. When a ticket is being closed, I can analyze the ticket with machine learning and check the sentiment of the interaction of my trouble ticket to see how the sentiment evolved from when the ticket was created up to the closing phase. You can synchronize data between your database and the provider. But the most important one for what I'm talking today is that you can, again, store and analyze all the events that you exchange in the event bus using Kinesis and S3. So it's a super interesting way to store and understand what is happening, not just from a technical perspective, but also from a business perspective in your application. So these are really my takeaways today. So building the instrumentation is a developer responsibility, and you should think about how to make it transparent. Mix technical and business metrics together to really understand what is happening. It's much easier to understand if a business metric is changing your technical ones. Use correlation ID and tracing to understand the flow of data, where are you spending time, and when you're getting maybe some errors. Think of machine learning as a way to process all this information that you can get better, and think of events as your source of truth. So in a serverless event-driven architecture, events can really tell you if and what is happening and understand if there are patterns that you can react to. Thank you. I forgot, those are also the partners that can help you set all the things that I was describing in an easy way, so that can really help you start faster.
Fantastic. Thanks very much.
Thank you.
That was awesome. I didn't know any of this.